Swayam Prabha. Digital India. Educated India.
If you recall, we were talking about the aluminium production through the electrolysis of Al2O3 in molten cryolite. And we also said that there were two kinds of technology that was in use. One was pre-baked, in which the anode is previously baked in the pre-baking furnace. And we also introduced a technology called Soderberg technology. Let me write. If you recall, the next technology that we discussed was Soderberg. And the difference between the Soderberg and pre-baked technology was that in this process we have the anode paste rather than baked anode. The idea was to use the energy or the heat available in the pot and use that energy to solidify or bake the anode rather than doing it somewhere else. So this picture, what you see in terms of A and B, they are both Soderberg technologies. Here this technology is called HAS and this is called VSS. What you see here, the number 2 here is the anode block. I won't call it block, but it is a system which contains the anode. So little hatch part that you are seeing here, this is the anode which is still in the form of the paste. As the anode comes into the contact with the molten cryolite, that's number 4, that's in here, it solidifies at this point, okay, and it solidifies, and then there's no previous baking that needs to be done. So this technology is called Soderberg technology. The idea is that it can probably save a lot of money in terms of the energy because we don't have to do any pre-baking. And you see here the rods are horizontal, okay, the rods which are bringing the current are horizontal. So that is what it's called, horizontal stud Soderberg. Similarly, if the rods are vertical, as you can see, the rods which are containing or bringing the current, okay, the vertical, so that is called vertical stud Soderberg. And thing is same again here, you have the green anode on top. As it goes down, it solidifies because of the high temperature available at the cryolite or the molten cryolite. And you see here, what is interest to us as the air pollution engineer or air pollution technologist is the collection of the emissions, okay, that is the part which is showing, and this is the emission collection. We are collecting all the emission that is occurring in the plant, and here was the emission collection, okay. So now you are fairly well in terms of understanding of what the Soderberg is. Well, we'll discuss what are the issues associated with the air quality when we are talking Soderberg vis-a-vis the pre-baked. I'll also quickly remind you what was the pre-baked, okay, although I showed you the slide, but again we'll have a very quick look. So here what you are seeing here is the anode blocks are already baked, and also the anode blocks are baked in the anode baking furnace, okay. So Now the issue is, this we discussed in great detail last time, but now you have clear understanding, or you can clearly differentiate between the pre-baked pot and the Soderberg pot. So let's go into something more as to how really these are the functional thing. So essentially this is a picture, again more of schematic. You see here the first thing which is done is the anode making. In the anode making, you essentially need the petroleum coke plus pitch. Okay, pitch is nothing but a binding material. Okay, so that it can make the coke, you know, in terms of, you know, like binding together, like it's like a cementing material basically. So first you do little heating of this area and you make the paste. Okay, and this paste is subject to, if it is a pre-baked kind of pot room you have, then it is baked first. You see here, after this dashed line, you see it's essentially a baking furnace. This area, as I'm trying to hatch it for you. Okay, but when you do the baking part, it causes some of the air pollution. Okay, and air pollution, as you recall last time we said, there can be VOCs, volatile organic compounds. There could be PHs, which are organic but not so volatile, some of them. You can also get some of the H2S. Okay, and some of the fluorides also you can get the emission from. So if it is a pre-baked kind of electrolyte cell, so that we send the pre-baked anode. But if it is a Soderberg type, okay, we don't do baking, and we hope that baking will be done in the pot room itself. So we don't do the baking, and before baking itself, we bring the thing which is still in the form of the paste. As you can see, the line which I am drawing along with the flow sheet is brought in there. Okay, so and then there's a from the electrolyte cell which is doing the electrolysis of Al2O3, it goes on to the pollution control device. But don't forget here that the emissions which were occurring in the baking furnace, okay, now these emissions, if I am following this stream, okay, again I repeat, we can follow this stream or we can follow this stream. Okay, if I am following this stream, the pollution is caused here, which can be emitted to the, after some control, it goes to the atmosphere. But if I am following this stream, I'm still have the pollution potential here, and then this pollution starts occurring from the pot itself. So now I will have the emissions of VOCs. Okay, I'll have the same emission of the PHs. Okay, and I'll have some emission of H2S and that sort of thing. So now the question is, this pot room is the area where lots of people work. So the air quality of the pot room is gets, if I can simply say, gets bad. Okay, and that can affect the workers which are there. So in fact, now the recent trend is not to follow the Soderberg process, not to follow the Soderberg, and go for the pre-baked, because in the baking furnace you can have it separately, and then where the people are not exposed. So this is, and apart from that, I don't have to mention, because we did last time, that we have to enter the alumina here, we have to enter the cryolite in the pot, and so is it, we have to put in the other salts and other fluorides for the electrolysis to be successful. Let's go to the next slide. So it's again repetition of what I said. In the pre-baked, what is the difference between pre-baked and Soderberg? Not from the technological point of view, but from the air pollution point of view, because that's what we are trying to address. So let's compare the pre-baked versus the Soderberg technology. Pre-baked gives you very good clean environment of the workplace. So the workers will be very happy, they are not exposed to the high pollution level. And the emissions will be there, but these emissions will be very small. Okay. Whereas in the Soderberg, the place is very dirty. Because why? There will be emissions of the hydrocarbons or volatile organic compounds, PHs, H2S, or some of the SO2, and that makes the working environment in the pot room very dirty. So now the latest trend is to, or the latest technology from, because of the air pollution point of view, from the public health point of view, for the workers which are working in the pot room, people go for more like pre-baked technology. Well, let's briefly summarize the two technologies and their difference, not only in the technological or the production point of view, as well as from the air pollution point of view. Okay, so far we talked about many things, but we haven't talked about the emissions that takes place from the pot. What I'm doing is I'm taking some small portion of the pot and really blowing it up, as you can see here. So you have the whole thing is like molten cryolite. Okay, see what happens, the temperature is in here is about 960 degrees Celsius. With this temperature, what we are expecting is some of the fluorides, because we are using the cryolite, we are using the calcium fluoride, we are using the sodium fluoride, some of the fluoride is at this temperature becomes volatile, as been seen here, or as it has been shown here. Some of the fluoride becomes volatile, and that tends to, and the pressure here, this is like kind of a crust. If you recall, we had said that, well, this is alumina crust, and then as the pressure is building up inside, because of the volatile compounds are emitting from the molten this thing, they tend to break open and get outside the pot. So there can be the emissions of volatile fluoride. Once this volatile fluoride comes out, then what happens in the process, you will have certain amount of water vapor. Where would the water vapor comes from? Well, some moisture is always there, and also we are also having some kind of hydrogen in the process. The anode, we may have some hydrogen associated with the carbon, and that can produce the water. So this fluoride, okay, this fluoride is which fluoride? The volatile fluoride that came out of the pot. That can quickly react with water, okay, and produce hydrogen fluoride acid, okay, that you see here, and this becomes a serious pollutant, okay, that is emitted out from the pot, and then it can cause serious problem. And remember, this is in the gaseous form, and this is very, very corrosive and very, very problematic from public health point of view. Okay, then what happens, apart from the gaseous thing which is coming out, which you see as G here, there is also a possibility that when these volatile compounds which are coming out from the pot room, as they reach in the cold area, see, this is very high temperature here, and there can be temperature could be, let's say, around 200 degrees Celsius. Okay, these volatile compounds of the fluoride, they quickly condense to form the particulate fluoride, okay, and then we can also, in addition to the in order to get the gaseous fluoride, we can also get the particulate fluoride. So let's write that we also get the particulate fluoride. Okay, so what we can say, if we can summarize, that a aluminium pot will produce both kinds of fluoride, which will be in the gaseous form, which will largely be HF, and also the particulate fluoride, which will be the various compounds of the fluoride. Okay, and then apart from that, this is a reaction that we discussed yesterday in the last lecture. This reaction was taking place, and then it can additionally produce, if the combustion is incomplete, it can produce CO, and of course CO2 will come. So now we have fairly good idea that, well, what will be the emissions from the pot room? There will be emissions will be largely that of fluoride, okay, and these emissions, to give you a little idea, the uncontrolled emission, let me write here to give you feel. Can be something like about approximately, we can't pinpoint the number here, but of the 10 kg of uncontrolled fluoride emission per ton of aluminium produced. And just to remind you here that we are constantly consuming the anode, okay, and the anode consumption is almost about 500 kg per ton of aluminium production. Some plants may have a little higher or some plants may have little lower. So what we have learnt is the fluoride is a key pollution problem from the aluminium production or aluminium smelting, if you like. So that's the word which we use. Okay, let's now from a blown up picture, let's go to a picture which is even to give more of bigger view of the things to us. So if you recall, if this is my pot, okay, and the pollution is occurring from the pot room, and it is going back and forth, it's going further to wherever the device where I want to take it. But you see here, if you recall, we used to have the covers here and the hoods. Okay, if you recall, we had the covers or hoods. These covers and hoods are not perfect, that they cannot, hold on to everything. There will be some leakages always. So these leakages, as you can see here, are shown this way. So something you can collect and some part you cannot collect. Okay. The part which you are able to collect and channelize, as you can see here, or follow my arrow, collect and channelize to pollution control device, that we'll discuss in a moment. These emissions are called primary emissions. Okay, the emissions which I cannot capture, okay, or somehow is not captured by the hood because of the leakages, they can open up in the room where you are working, or they can open up in the pot room, and they are called, you can see here, secondary emissions, which goes into pot room, as we can see. So they will follow some pattern and go up, not only because the temperature is high, but also you may have some kind of fan here to suck these emissions. Otherwise the emission concentration will become very, very large in the pot room, and it can become very difficult for the operators, the working force. They will be very much disturbed because of the high pollution. So you provide a fan. This fan essentially, either it can be natural draft also, but many plants will provide fan. It provides good ventilation in the pot room. So now what we have done is that now we have introduced another concept here, that the primary emissions are there and also there are secondary emissions, and we need to handle both of them because both are pollution for us. So when we talk about the handling of these emissions, the first part, I'll again repeat, is a proper collection. Okay, the one which is collected goes through some kind of scrubbing system. It could be wet scrubbing system, okay, and there is a dry scrubbing system. And don't forget, our objective of any scrubbing is the removal, also we should say recovery of fluoride. Okay, so before now I would like to explain to you that some more terminologies before we go to the scrubbing system. This is generally we like to write Ft as a total fluoride. Okay, why total fluoride? Because it has two components. One is the particulate component and the gaseous component, as we described in our earlier slides. So Ft, which is the total fluoride. Okay, now we are talking about Ft is now this Ft which we are referring here is the kind of emission, if we can say, uncontrolled emission, uncontrolled, okay. So Ft can be from primary, some part will come from primary emission, there will be some part that will come from the secondary emission. So within the group there will be some part that Ft is further divided, some part will be from the particulate and some will be from gaseous. Again, some will be particulate, some from the gaseous, but that are from the secondary emissions. Okay, and always remember, in the aluminum plant, the basic units through which we work always is more of a convention. Of course, you can change them, but more of the convention is we work through the fluoride emissions, fluoride requirement, anything in terms of kg of fluoride, and that is rather kg of total fluoride per ton of aluminum produced. So this is kind of gives us this basic unit through which we work through. Okay. Let me also show the same thing what we discussed through the actual schematic. As you can see here, these are the pots and these are the secondary emissions that are taking place. Okay, and this is the fan which I was referring to. Okay, and then when it comes to the control, not only the primary emission that is controlled, okay, the primary collections that will occur. Okay, the primary emissions will be collected here as I was referring to the figure. Even the emissions which are collected through the fan, which we call as a secondary thing, is passed through a control device. Okay, so what you can see, the primary can go to another process. Okay, here the secondary also, once they are collected, they can also be treated, and you can see there's some kind of tower where some chemical in the form of the liquid is falling down. Okay, and we'll see this thing. I'll probably explain you a little bit more about the wet scrubber. So quickly what I want to do is I want to explain to you what is the wet scrubber. And this wet scrubber is for the removal of fluoride, the total fluoride. The system is very simple. Okay, first of all, whatever the primary collection of the fluoride that you are bringing in from the pot, you pass through a device for the control of particulate, and we call that as ESP, and ESP stands for electrostatic precipitator, so that most of the particles are removed. So let's write particles are removed, and then the stream which has now the gaseous fluoride is passed through a chamber. Let me draw this picture for you through the chamber. The dirty air, which still has a gaseous component, okay, is passed through here and it travels up inside a chamber. And in the chamber, what we do is we spray some chemical that I'll explain you through the nozzles. So this is a nozzle. Again, there is an opening and there is a nozzle. Okay. Okay, nozzle is something you can think of shower. We all take shower in the bathroom. So the shower is something with the fine droplets like the waterfalls in the shower in the bathroom. So there's something like we are having little showers. There are many showers. They are making very fine droplets of the liquid, and this gases, okay, and this falling liquid. Come in very close contact. There are little liquid droplets, okay, and then they can react in the process. And what is this chemical that we are using here? We are using the solution of Na2CO3. Okay, so this some Na2CO3 solution is prepared and then it is pushed through this one. So after this contact, the hydrogen fluoride will be removed, because hydrogen fluoride is largely in the gaseous form, if you recall. So what the reaction that might take place is HF plus Na2CO3 is that you are producing sodium fluoride plus sodium bicarbonate. Okay, so what you have succeeded in doing this, that this gaseous component you have brought that into the liquid component. Okay, as a result, what you will get, the outside of this chamber, as I was trying to show, will be the clean gas. Okay, then what we do is this, we have to still recover the fluoride from here. So this NaF, this liquid, okay, which is this liquid here that is now passing out, we send to something, a process called cryolite, because that's we always required in the pot recovery. Okay, so we need to recover this one, and then how we do this recovery is that whatever this liquid, which is, this is same as this, don't forget that. Okay, so that we have NaHCO3 is reacted with sodium, some kind of Al2O3 with the molecules of Na2O, okay, that we make it react with. So once we react with this one, what eventually the reaction is completed. So I must get the cryolite, because that's what I want to recover. What was the chloride, if you call? This was my cryolite, and cryolite is formed, and in the process I recover back my Na2CO3, which I need to recycle again, plus some amount of water. Let's balance the whole thing. You get here, you probably need 6 here, and then you need to have 12, and then here you probably will need 2, and it's 6 here, 12, and then you are getting here, so this also becomes 6. Okay, so you can balance the thing, and then finally what you're recovering really is your, okay, you're recovering your cryolite. Okay, and there are certain issues with the wet scrubbing process, and that process is we have to see that these processes are, these difficulties of the wet scrubbing are taken care of, otherwise there can be a serious problem with this one. Okay, let me correct the number here. If I am doing the balancing, this should be 12, and then you also this is 2 is fine, and so okay, the main thing is that we are recovering the cryolite here. So if I go on and say what are the issues and difficulties or disadvantage, disadvantages of wet method. See, one thing it did little problem is it converted the air pollution into water pollution. Okay, and so you need to have the wastewater. WW stands for wastewater treatment plant. And if you don't have, for example, the ESP or the particulate control is not efficient in wet scrubber. Okay. The other thing is there is a sodium built up, as you can see here. Built up, that caused little problem in the pot. Why the sodium built up caused a problem in the pot is because it affects the very processing in the pot room, and you might have little difficulty with the quality of production of the aluminium. The other little problem which people refer to, some of the SO2 is also removed in the process. Okay, why? Because it can react with Na2CO3. Well, in a way it's good that SO2 is removed, but this causes the level of total dissolved solids in the liquid that is coming out from the treatment plant or the cryolite recovery plant. This becomes very high, and this becomes a problem for disposal. Okay, so what we have done is we have understood the wet method and wet processing, but it is not perfect. It has its own problems and difficulties. So the people thought about the different technologies and different methods. So we'll see the other technology. So what I'll do is I'll remove this and talk about the other technology that we call as the dry scrubbing. Dry scrubbing is very interesting, efficient, and very useful, because it can recover almost the entire fluoride from the process, and most of the new plants will always have the dry scrubbing rather than the wet scrubbing. So, well, the idea was very nice idea as to about the dry scrubbing. So let's discuss about the dry scrubbing, so that we don't need any water, liquid, or even any chemical, because you see the use of the chemical will always make the things more expensive. So the idea was that if you look at Al2O3 from calciner or let me say calcinated, if I look at the particle of Al2O3, the particle is not like this. Okay, in fact, I look the same size of the particle will be something like this. So what it is really saying is the surface area, okay, is very large. Is very large of activated alumina or calcined alumina. So if the surface area is very large, then we can use the surface area to absorb the HF. Okay, and in fact the reaction or the absorption of HF onto this Al2O3, which is highly activated, is very quick and very efficient. So what we say, if we are having the HF plus alumina particle, it goes through what we call as a chemisorption. If the same particle, I am trying to do this one, and along with this the HF will absorb. So this is my HF, which was, you remember, that was gas, and this is the Al2O3 is a particle. Because of the large surface area, things tend to absorb on this one. And then this is what is the technology which is used. The advantage is okay. See, the interesting part is that, well, alumina is already available to you because it itself is a raw material. So you don't have to bring in anything from outside to be able to control the emissions. So it is already a raw material. So that's a very healthy situation, happy situation that you have in the aluminium. Raw material is available, raw material available. It's always available to you. Okay. And then what is happening is, this good thing about this HF, which was in the gas, goes into the particulate form. Okay. And the control of the particulate is a little simpler sometimes. So you can capture it through the back filters. So in a way, and then once it is captured, the whole thing can be recycled in the pot. Or if I may say so, the pots are always hungry with the fluoride. They need more and more fluoride. So if you can capture the fluoride, put it back onto the pot, you are almost 100% recycling the fluoride, and that makes the operation even more cost effective. So now what is happening is, most of the plants in the aluminium industry, they will have the dry scrubbing thing. It is almost, it's not relatively still new technology, it's about probably 30 years old technology now. So every new plant, or in fact the older plant also, if they can quickly somehow shift, they would rather shift to the dry scrubbing technology. And to give you a little feel, the surface area here, okay, of the alumina is around anywhere like from 30 to 45 meters square per gram. So you can imagine the amount of surface area that is available for adsorption, or in fact we call it chemisorption, is very, very high. Okay. So having said about the dry scrubbing, we would like to show you a picture about the dry scrubbing. And this is a, in fact this is being used, we have taken this picture from the from a company, from the available literature, but what you see here is very interesting part. So if you recall, all the dirty gases, which are lots of fluoride, okay, is coming from the pot room, and then you can see it's written as a pot gases. So what you remember, this will have Fg and it will have the Fp. Okay, it enters from here. Okay, there is a blower, and then what you can see here, there are little openings here. Okay, distributed openings, so that the pot gases can pass through these openings, as you can see them. Okay, and the alumina, which is from the calciner or activated alumina, that is available because this is raw material. Okay, that also is pushed through this mechanism, which is rotary feeding unit, and it is put onto the perforated bed. See here, the little small openings. Here the openings were large, and here openings are small. So these are the perforated opening, and then this gets distributed all through. Okay, and then this becomes a fluidized bed. Okay, bed, and the dirty gases comes through this one, and then they come into contact with the Al2O3 or the alumina. Okay, so gases comes here, and then they kind of mix with these things. Okay, and HF continuously get absorbed onto these alumina particles. Okay, and the fluidized bed is the things are, it really means is something that alumina is somewhat little bit as if it is slightly floating. Okay, or you can take to understand this fluidized bed is more like, you can think of the popcorn, you know, like large surface area and they're little popping up slowly. So they're just slightly in suspension, tend to become in suspension, and then as a result the entire surface area is available for the absorption. Okay, but then they are still in particle form. So over and above this one we have the back filters. So what you see here are really shown as the the fabric bags. Okay. Okay. So here you see here, this is the bag and this is the outside the bag. Okay. So the fluoride rich alumina goes and then it passes through the bag and it become clean, and you see here this side is clean, this comes out. Similarly, this is the dirty portion, goes through the fabric filter and then is coming out more like a clean gas. So everywhere you're seeing the little dots here, this is the clean air that is coming out. Okay. And this is the bags, okay, in which the fluoride will be trapped. And then this thing is taken out, the alumina. Okay. And this alumina, don't forget, this alumina is rich with HF, because that we have completely removed it. So what we have done is we have not used any other chemical, and yet we are able to capture almost the entire amount of the fluoride. And the question for you is where this will go. This should go back to the pot, because we need alumina in the pot, we need fluoride in the pot. So the natural choice for this one is to send it back to the pot room. So this is what is a dry scrubbing method. We are not using any water and things works very, very efficiently. Okay, so this is clear. Then I want to make a little example and some kind of little bit efficiency derived thing. Okay, this figure what you are seeing here is a summary of the gas cleaning process in the aluminium industry. What you are seeing here is the silo for alumina, okay, activated alumina that you have here. Okay, and this is where the emissions are coming from the pot rooms. Okay, and here we are talking gaseous fluoride and the particulate fluoride. Okay, and this, with this storage of Al2O3, this is pushed into the gas cleaning plant, and then you remember this was the fluidized bed reactor which we discussed. So this gas is the polluting or the dirty gas, if I can call, is pushed through this reactor. There is a chemical reaction that takes place. HF is absorbed onto the particles, okay, and then the particles are controlled from the back filters. This is a little section which you are seeing are the back filters inside this one. And after the things are cleaned through the bag, the clean gases are discharged to the atmosphere. Okay, and now the rich alumina, which was rich with the fluoride, now is collected from this end. Okay, and then it is taken and stored in this tank. Okay, here what you can see here clearly is the it says rich alumina storage, and now this can go to the pot room. So, and then from again the emissions from the pot room comes this way, and this kind of recycling cycle continues, and as a result almost I'm able to do that. Fluoride is sustained, is kind of more like watertight, it cannot escape or disappear, and that makes the process very efficient and very advantageous. So this was a little dry scrubbing thing that we seen, and dry scrubbing has overcomes all the issues and the problem with the wet scrubbing. So this again you can see the picture where clearly everything is completely recycled. Okay, now what I would do is derive some expression to say what are the total emissions that can take place from the aluminium plant. Recall that we have discussed there are two kinds of emissions that are taking place. One is the primary emissions, Okay, and if I can divide this, then there are secondary emissions. Okay, then the final emission, okay, is the sum of the primary and secondary emission after it has been controlled to the extent it is possible to do. Okay, maybe it might be a good idea to quickly go back and maybe see some of the slides here, but well, you recall what is the primary and secondary emissions. So if I say the primary emission is, the total emission is Fg and Fp from the pot. Okay, so what will happen in the primary process, certain part of this emission will be collected, or at the hoods it will be collected. So suppose the collection efficiency I'll write that as eta and call it C, eta C. The collection efficiency is eta C. This suggests that amount of fluoride that will be captured through the hoods. Okay, so let me write uncontrolled primary emission, and I'm assuming this collection efficiency is the same for the gaseous fluoride as well as for the particulate fluoride. So the collection part, since the efficiency is the same, okay, Fp. Okay, now if this what is collected at the hood, whatever is not collected, that goes out as a secondary emission. So let's say corresponding to this, the emissions in the secondary emissions will be, if I can show the arrow here, will be whatever is not collected. What is not collected? 1 minus the collection efficiency is not collected, because eta C was the one which was collected. So we can say here that is equal to thing which is not collected fair enough. Then what we can do is, now this, once it is uncontrolled, but now we want to treat it or clean it. So now let's say the controlled emissions. Let's say the control or removal. So let me call eta R as my removal efficiency, of fluoride, and I'm assuming that removal efficiency is the same for gaseous as well as the particulate fluoride. So if this is the removal efficiency, the emission will be 1 minus but this is at the primary thing, so let's write at PR if you like. Okay, and this is the amount which will be emitted from the primary gas cleaning device. So that will be eta C Fg plus eta C Fp. Okay, the removal efficiency at the secondary process or the secondary device can be different. So okay, so let's say eta, so that is eta R is different at secondary treatment. So now controlled emission 1 minus eta r, and this is where at the secondary level. So I put subscript the secondary, and this was the total emission uncontrolled, and this is the emission after the controlling. So let's complete this. So what we have been able to say is a controlled emission relating to primary and controlled emission relating to secondary. Let me call this as A, and let me call this as B. Okay. So therefore the total emission of fluoride which is occurring from the plant is simply A plus B, total fluoride from the plant is A, that is from the primary, plus B, that is from secondary. That is all I need to know. So this is what, when we talk about the total emission that is occurring from the pot room, then we have to do both summation of A plus B. So what we'll do is we'll do an example here to demonstrate as to how this, the little expression, the simple expression that we have developed can be utilized in assisting or in knowing what is the total emission occurring from a aluminium plant. So we'll go up here, or we should go down. Okay. The question is for you is, let's say, a problem. An aluminium plant of capacity ton per year is operating both primary and secondary treatment for fluoride control. Determine if it is complying with emission standard of 3 kg of total fluoride per ton of aluminium produced, because there will be some norm, there will be some standard given by the pollution control board or pollution control authorities, and then we have to see the details that are available to you is FG, total FG, okay, from the pot is 10 kg per ton of aluminium. FP is also 10 kg per ton. Okay, the collection efficiency is, let's say, 0.8 collection efficiency at the hoods. Okay, and collection the removal efficiency at the at the primary, I think PR is 0.9 or 90%, and removal efficiency are at secondary is, let's say, 0.5. Okay, that is the information that is given to you, and now you have to find out the emissions. So what I'll do is that I'll do for you the primary emissions first. uncontrolled emission will be Fg plus Fp, and only 80% is collected. So because the collection efficiency is only 80%, so I can write 0.8, okay, and out of this, okay, 90% is removed. See here I am given 90. So what will be the emission? One minus 0.9. Let me make it even better for you. Okay, so this is primary emissions. Okay, the secondary emissions will be so let's find this one out. First we can calculate the primary emission. So this is your, this will be your 0.1 times Fp plus Fg is 20 into 0.8, and this has to be 1.6 kg per ton. Okay, now let's look at the secondary emission. Okay, so secondary emissions are basically 1 minus 0.8, because this is the portion which was not collected by the primary, so this becomes the part of the secondary. Fp plus Fg, okay, and out of this the control is only about 0.5%, so equal to 0.5. Simplify this, so this is 0.2 times 10 plus 10, 20 plus 0.5, so this makes it, okay, how much does it make? That makes it 2 kg per ton of aluminum. Okay, this is from the secondary. So the total emission that is occurring from the plant is, this was, if I recall, this is my A and this is my B. The total emission A plus B, so that is 1.6 plus 2, that makes it 3.6 kg per ton of aluminium produced. And what was my standard? My standard was 3 kg, that prescribed by the whatever the pollution control authorities. So what I conclude, well, my treatment devices are not able to comply with the emission standard. My emission standard was 3 kg and actually the plant is emitting 3.6. So to specifically answer the question, no, the plant is not able to comply with the emission standard. And obviously then there will be questions, so well, if it cannot comply, what you can do? Then what you can do is, the best thing to try to really do is to improve the collection efficiency. Make your pots more tighter, so that more and more gases are collected. If you are able to increase from 0.8 to 0.9, for example, you make it 0.9 and you see everything is falling in place and you are able to control the things. If you want, we can certainly do this calculations all over again, and you will see things will fall in this way. So this is how you can do the final calculation for your aluminium plant, and you can see if the aluminium plant will comply with the standard, what are the changes that you need to make in your process, what are the changes that you need to make in your control devices, and that, because this sometimes the standards are very legalistic requirement, and this is the procedure through which you go through the calculations and things like that. So this ends the fluoride emissions and issue of pollution, or particularly the air pollution from the aluminium plant.